Alright, silly people. Here's the situation. This time we are checking if these various different operators commute. Um, where T, subscript D, um, is a translation operator, which, when applied to quantum state X prime, will just move it forward a bit by a distance vector D. Um, Big D of n and phi is a rotation operator, which, when you multiply it by quantum state x prime, will give you um, x prime prime. Okay. Um, then the pi is the parity operator, which just flips the sign of a quantum state. Right. Oops. So let's check the commutators then. Uh, First, TD with TD prime, where the D prime indicates that it's going to be moving forward a different by a different displacement vector, um, minus TD prime times TD. Um, we can multiply this by a complete set of states. In fact, I'm going to be doing that for all of these problems. Because you can, and it makes the commutators easy to read. Um, the complete set of states being x prime, x prime. So moving in one of those, moving in the ket x prime, we'll have t d prime x prime minus t d prime t d x prime, and then the bra on the outside there. The translation operator on the left term will move it forward by a displacement d prime, and the displacement operator on the right will move it forward by a distance d. Okay. Um, then applying the operators again, now we just have TD. It's going to move it forward by a vector D this time, so D prime plus D. And then this one is going to move it forward by a displacement vector D prime, D plus D prime, which these quantum states do actually match. So this is 0. So two translations commute with each other. Makes sense. What about rotations? Do rotation do rotation operators actually commute? Um, this is kind of a trick question. Um, the answer is a hard no. The rotation operators just don't commute. That's because each rotation is going to end up being the rotation matrix, uh, which is cosine phi minus sine phi cosine phi 0, 0, 0. Which, whenever you do it again, if you multiply um, that operator by another rotation operator, it's generally not going to be the same as the other way around because matrix multiplication isn't communicative like that. Um, for the general case of phi and phi prime. So this one's definitely zero, or definitely not zero. These guys don't commute. For the translation operator and the I already forgot what this is called. What's it called? A parity operator? Yeah, okay. Translation and parity. Um, which, like before, is just td pi minus pi td. We can multiply it by a complete set of states. I'm going to go ahead and move the ket inside. So I'll have pi x prime minus, yeah, pi td ket x prime bra x prime. All right, the on the left term, the parity operator is going to actually change the sign of the state vector, and then on the right term, uh, you're going to end up just adding to the state vector a displacement vector d. Okay. Um, going again, same thing as before. The translation is going to add a displacement vector, and the parity operator is going to change the sign of everything inside. Those are two different state vectors. That means that this is not equal to 0, so they don't commute. Moving on to, does rotation commute with parity? Well, let's see. We're going to have d prime pi minus pi d prime multiplied by a complete set of states. Ooh. Pi d prime x prime x prime. Whenever we operate with parity, it's just going to change the sign. So x minus x prime, and then when we rotate, you'll end up with x pointing in a different direction, x prime prime. Then again, when we rotate, the x is going to be pointing in a new direction, x prime prime still minus, and then the parity is going to flip the sign of this state vector. In that case, we do actually end up having two of the same state vectors. So that is 0. So parity and rotation do commute.